All right, would y'all mind if we pause the quiz and then we can do lecture, and then obviously you can come back to it. So yeah, feel free to hang on to the quiz unless you're done, of course. But yeah, I just want to get our lecture done so we can talk about the rest of this, so calculating our yield, and then probably look at some of the lab stuff. So again, I super apologize. I don't know what to say. This cord is on its last limb, and apparently it takes like literally 30 minutes for me to like position it properly. So again, I greatly apologize. But if you want your lecture streamed, then this is the price you pay. So take that with a grain. So yeah, if you don't like it, I can always start not streaming. But I assume everyone likes it. All right, so we left off on this problem. So maybe take a minute or two to kind of look at this. And so if you kind of remember, and let's maybe refresh on our steps of what we're trying to do, right? So usually we're given some mass, and this is a good refresher for today's lab, right? You are either finding the mass of magnesium sulfate maybe, or right, your mass of water, converting it to moles. Later you can do your mole ratio and figure out, right, your theoretical percent yield. And then I have extra mole highway chart if anybody needs. Orient yourself. All right, so let's start going through this together. And so remember, right, this is technically a limiting reagent problem. So we're going to have to do this whole stoichiometry business twice, right? Because first we have to figure out, well, what's my max potential yield with this amount of NO? What's my max potential yield given this amount of hydrogen, right? Find the smallest, and then that is our theoretical yield. And so let's go through that. So, oops. So 86.3 grams of NO. So divide by the molecular weight, which I think we said was 29.99 from last time. Again, you could kind of add it up, right? 14 plus 16 from the periodic table. Again, some rounding discrepancies will occur. All right, so that gives us moles of NO. And then for this one, so I would compare, right, our NO and ammonia ratios. It's kind of the easiest, right, because we want to see, again, how much product. And you could simplify, right, they're in a 1-to-1 ratio. I'll just be explicit and write 2NO is equal to 2 ammonia. And then they want us to get the yield in grams. So we might as well set up the last step. So 17 grams per mole. So do we have a theoretical yield for our nitrogen monoxide? So I get 48.9 grams of ammonia. So what other people got, or at least close to this, right? So about 49 roughly. And so then let's repeat that, right? So we need to see, is this our limiting reagent or not? So same steps, just now with hydrogen. So H2, so again with 25.6 grams, divide by our molecular weight of roughly 2. And so now when we compare, it's a 5-to-2 ratio. So just watch that. So, okay, for every 5 moles of hydrogen, we can produce 2 of ammonia, and then, of course, convert it back to a mass again. And so let's compare. And so now I get a theoretical yield of about 87 grams. So now which one is our least amount? Which one's our limiting reagent? Yeah, the one on top, right? Not a trick question. So just compare, right? Which one's smaller? Okay, this one is the smallest amount. So of course that is telling us NO is going to run out first. So we could say that nitrogen monoxide is our limiting reagent then. And then of course this is our yield, right? Or again, our theoretical yield. Good. All right, questions on that one? So I was going to pull up your lab so we could look at some of those questions. Sorry, give me 1 second. All right, so let's look at the post-lab question, and I'll paste it in a second here. And so I know a few people tried it, but let's do it together. This is a good one. So we have, again, very similar experiment to what we did. And so now a student heats up 4.75 grams of copper 2 sulfate pentahydrate. And then at the end of the experiment, they have 2.82 grams of the anhydrous copper sulfate. And so try to figure out a theoretical yield. So try this, like I said, for a minute or two. I know some of y'all already attempted it, and then we'll go over it. And so again, right, start with that balanced equation, kind of thinking too what you will be doing. All right, so let's help me with this. So we have our reaction, and of course, right, copper 2 sulfate, so CuSO4, that looks good, right? The sulfate has a 2- charge, and then they told us it's pentahydrate, and now we can write our reaction, so plus 5 equivalents of water. And so what information do we need to start with to calculate our theoretical yield?
The mix of the hydrate.
Excellent. So what do we find for our pentahydrate?
The molecular weight is 249.72 grams.
249.72.
Yeah.
And then, so Bray, I see you nodding in the back. I remember you were doing, that's what you got too, right? Because I remember you calculated that. All right, so good. And right, make sure that you accounted for those 5 equivalents of water when calculating for the molecular weight. So right, you add up your copper sulfate like normal, and then you can do 18 times 5 and add that to that. All right, good. So now we can proceed, right? This is a regular stoichiometry problem now. So we have 4.75 grams of our copper sulfate pentahydrate. Let's figure out how many moles that is. And then of course, right, they're in a 1-to-1 mole ratio. I'll write that just to be, again, super explicit. So every 1 mole of hydrate gives us 1 mole of anhydrous. Oh, and then we need, what's the molecular weight of the anhydrous? Does anyone have that? 159.62. Is that what? Okay, good. I see some more confirmation. Just checking. So this is looking good here. Now let's just plug it in to our calculator. And so then we should get about 3.03 grams or 3.04 depending on your rounding. I'll put both numbers. Again, just kind of, I think we technically got 3.04 with our rounding here. And so now we can get our theoretical yield. So right, this is, or excuse me, our percent yield. So right, this is our theoretical. Again, label that if you need. Okay, that's our theoretical. Again, write what we expect, perfect conditions. And so now we can take this 2.82 grams, again, what we actually recovered, so what you actually got in your beaker or your crucible, divided by the theoretical. And so then we should get about a 93% yield or so. So I left mine with 3 sig figs. All right, so that one's not too bad. And so then for the other ones, just make sure, right, you're using your balanced equation for part 2, for post-lab 2 and 3, right? So I'll just say that, use your equation. Honestly, I think this class did pretty well on your data from what I saw. So kind of the correct expected answer should be like 7 equivalents of water. But honestly, every year when we do it, most people get 6. And I just always tell people, right, just use your data. But if y'all got 7, you know, that's great. So, right, I'll just kind of at least outline it roughly. So then if y'all got 7, then it should look something like this, right? Otherwise, I'll just put other possibilities. And so just show your work and everything. Because again, I'll base it off of your data. So if you ended up with 6 equivalents, which I don't know if anybody in here did, then just use it, right? Because again, it's your data. Otherwise, you know, use 7, so whichever one matches. And then I calculate, right, the molecular weight appropriately and get your theoretical yield. All right, let's look at some of the homework problems. So that one has a few things we haven't quite covered. Oops. So let's see, let's look at, yeah, let's calculate. We'll start with this one, and then I'll show you some modified ones. So see if we can calculate this one. So we didn't do this in class necessarily explicitly, but we do have our mole highway, so that's kind of why we're going over it today. So right, we have our mole highway, we have Avogadro's number, and this conversion factor. So that's on your sheet down here, if you didn't write it, 6.022 times 10 to the 23rd. So going back to our homework, right, what is this asking us to do? And think about your mole safe space as well.
Do we have the product equation for that, or it's just a random question?
Just like, yeah, a random question. So yeah, look at your conversion factors though, right? What is it asking? What are we given? Kind of look, like I said, look at your mole highway. And so I'll give a hint, right, as we look at our mole highway. So yeah, right, it's telling us to calculate how many molecules are in 100 grams of oxygen. So kind of, if we're looking for inspiration from our mole highway, right, well, we are given grams, but we want particles down here. So then kind of following this, okay, we need to go from mass to moles to particles. And then, right, it reminds us, oh yeah, I need to divide by my molecular weight. And then keep in mind, so this is where we're going to do another example to look at the differences. But this one, right, we are talking about diatomic O2, so we should use O2 in calculating the molecular weight. So I'll give people another minute or so to work it out, and then we'll go over it. So what do we have to do for this one? So again, we started with 100 grams of O2, and then what?
For every mole of 32 grams of oxygen.
So there's 2 atoms of oxygen, so then what's our molecular weight?
31.998.
So 31.998, we could round to 32. Again, right, discrepancies are fine. So for every 1 mole of O2. So excellent, so that gives us moles then of O2. But again, it's asking for molecules. So now we can multiply by Avogadro's number. So 6.022 times 10 to the 23rd molecules is equivalent to 1 mole of any substance. And so now we can punch it all in. So 100 divided by 32. So we should get about 3 moles, and then multiply by Avogadro's number. And so something like 1.88 times 10 to the 24th molecules. All right, so let's look at some other scenarios. And so let's look at just another problem. So we're going to say aspirin has a molecular weight of 180.159 grams per mole, and a formula of C9H8O4. And so if a sample is 39.56 grams of aspirin, how many molecules is this? So let's just start going through it. So what do we have to do for this one? So grams to moles. So we're given this many grams, and then I decided to be nice and give you the molecular weights. You don't otherwise, right? You can add up 12 times 9 plus 8 plus 16 times 4, yada, yada, yada. So excellent. So we find our moles. And then where do we go from here? Sounds good. So moles, and now Avogadro's number. So let's see what we get. So 39.56 divided by our molecular weight. So about 0.22 moles, and then multiply that by our Avogadro's number. All right, so then we should have this many molecules, so 1.32 times 10 to the 23rd roughly. So I see some nods. And so now let's take this
your answer for the molecule?
Oh, sorry. 1.32. All right, so now let's take this to the next step. So first we asked how many molecules, but what if we want to say, so how many oxygen atoms are present? So kind of think of what you found, kind of think of what this means, right? How many oxygens are in here? So yeah, just think about it for a minute or so, and we'll go over it. All right, so did we kind of figure out maybe what to do slash what we're kind of saying? Yeah, really a lot of sirens today. But basically, right, what we want to realize is, okay, well, this is one molecule of aspirin. And then for our purposes, right, if we're interested in oxygen atoms, well, now we can set up our ratio. So for every one molecule of aspirin, right, we have 4 atoms of oxygen. And so this is where I was saying, right, now we're just talking about individual oxygens. So we're just looking at, right, single oxygen. So just, again, keep that in mind depending on the scenario. Jeez, what is going on out there? I know, it's like I haven't heard that siren before. Yeah, now we all have ADD. I can't tell.
I'm curious.
Yeah, it's like I kind of see something, but I don't know what's making that crazy noise. Oh, there's the cop walking off the. Damn.
What happened now?
Yeah, that
I
is
think those
nuts.
2 bangs that we heard earlier.
I didn't even notice any bangs.
Tweaking,
Oh.
tweaking. Yeah.
Anyways.
Well, I'm not getting home. They're walking off my exit.
Anyways, never a dull moment in downtown, I guess. But basically, right, we would just want to be able to establish our ratio then. So of course, again, we're talking about oxygen, but we could do that for carbon, for hydrogen. And so then we can start with our 1.32 times 10 to the 23rd molecules of aspirin. And then multiply it by 4. Again, just using our relationship that, yes, there are 4 atoms of oxygen for every 1 aspirin. And so then, of course, we can just take our previous answer, right, since we already did all the work of finding moles and molecules. So now we can just multiply it by 4 and say we have 5.29 times 10 to the 23rd oxygen atoms. questions on that one? Yeah. All right. So I know we all have ADD now, but. So I did want to point out, so I posted this resource on Blackboard. So it's here. So I'll show it. So there's a link to Everett Community College. They just have a lot of nice practice problems. And so this is a good chapter to maybe explore this, and we can try some of these. Of course they have a whole bunch of problems on here, but let's look at these stoichiometry ones. The only thing I will caution y'all on is I have seen mistakes on their answer keys before, so if you don't agree with their answer, maybe just check their key and see, because usually it's like a molecular weight error, so you can kind of see what went wrong on their answer key. But obviously you can ask me if you have issues. But let's try this one. This is a good one to do. And like I said, you can look at other ones. They have other stoichiometry and all sorts of practice problems. Yeah, actually, some of these word equations are good. Oh, that's not what I was looking for. But yeah, let's just do this one. Let me copy it over. Sorry, so I'll copy it and then you can finish writing it. And so let's just start with those first two there. What the? Oh.
She was looking like she wanted to say something and then she just walked off.
Oh, I'll go poke my head out. But yeah, look at this one. Oh, wait, let's not do this one. I'm sorry. I just realized it had a molarity calculation, which we don't know how to do. So let me find another one. There we go. All right, so let's try this one now. Sorry. No, we'll do molarities later. So of course, it's not balanced. Damn, more sirens. So start by balancing it, and then we'll try and check in, make sure it's balanced, and then I'll let you loose. So before everybody gets too wrapped up, so what do we need to do to balance this? What coefficient should I put and where? So 2 to the H2O, and then just kind of double checking that. So okay, so 2 and 2, so 4 hydrogens, that looks good. our sulfates stay together, and then we just have 2 oxygens. All right, so that looks balanced. And so now I'll give you all another minute or so to try to answer this then. So let's see how this one is going. So what do we have to do? What extra info do we need to?
Molar weight of calcium sulfate and calcium hydroxide.
Excellent. So what do we get? Let's start with calcium hydroxide. What do people get for the molecular weight?
Grams.
74.1 grams per mole. That sounds good. Is that what other people got roughly? So yes, excellent. And then calcium sulfate, what do we get? Minna, do you have an answer? Yes. add them up. So what's calcium, like 40 plus sulfur, which is 32, plus 4 times 16, so what do we get?
136.15.
So I hear 136.15. Got people like that, so I see some confirmation. All right, good, so we got our molecular weights, right? And so think about too, on like your upcoming final, I mean, it's not coming for a while, but it'll be here before we know it, but right, so part of this, partial credit is being able to calculate that. So kind of keep that in mind, especially for test strategies. So that's one thing that I noticed with like the tests, it's like either people did like really stellar and then people like didn't do as stellar. But part of like, test taking is being able to kind of like bullshit a little bit too. And like, my old teacher had a saying, right? It's like you got to blow smoke up the professor's, she's a different word, but, right? So like it's the same sort of thing. You want to show, okay, here's like some formulas. And so that's like my tip for y'all, because, my exam is probably easy, even though it may seem hard, but like if you go on to like other math and science courses, like they're not going to get easier. They're going to be free response exams just staring at you. So you got to get used to that, just kind of blowing some smoke, up your professor's butt and showing some formulas, showing some steps, right? So this are good ways to earn little points is what I'm saying, right? It's like show every little step. It's like, okay, so we got our molecular weights, right? That's a good step there. And so, yeah, so for the future, throw formulas on there, try to get some partial credit, because that's also what's killing, students. It's just like, if there's nothing there, then I can't even, like, try to conjure up points. But anyways, so continuing. So, okay, so what are we given? So we have 130 grams of calcium hydroxide. Luckily, excess sulfuric acid, right? So we don't have to worry about doing a limiting reagent problem. But let's finish it. So 130 grams of calcium hydroxide, divide by our molecular weight. And then again, mole-mole ratio. So we want to compare, so calcium sulfate, so 1 to 1, so that's nice at least. And I'll just write it. And then last step, right, multiply by our molecular weight. And so let's see what we get. So 130 divided by 74.1. So 1.75 moles of calcium hydroxide. And then 1 to 1 ratio times our molecular weight. So about 238 grams or we only have 2 sig figs. So most appropriately would be 240 grams. So something like that. All right, I think we have caught up with our lecture time. Unless there are any other questions or things you want to go over. Let me just glance at the homework again. Yeah, we didn't do this one, but I think this one you could try on your own. So again, right, just it tells you what a trillion is, calculate the mass of this. So maybe what you could do is kind of put this in a mole ratio, right? So if it's 1 times 10 to the 14, put it over Avogadro's number. and you could get how many moles that was. So that's probably the only other hard one. So I'll put that here and give a hint to the setup. But otherwise, I think that mainly covers it for the chapter. So just kind of practicing the stoichiometry. And so of course stoichiometry won't go away. So we'll also be there with molarity and solutions. So yeah, go ahead and finish up your quiz, and then obviously, right, we can take the rest of the time to work on anything else, ask me questions, practice, practice, practice your stoichiometry. Really, stoichiometry is just like a ton of repetition. So just do it a billion times until you're super comfortable. Have a good weekend.